So today we are on the second session on the topic of cardioid, and we looked at the cardioid as a locus that is created by the movement of circles in a specific pattern. We also looked at it as an envelope that is created when a set of circles are created from a base circle that is shown here. And previously, we looked at how a cardioid could be generated. Today, we'll move forward and look at the polar equations. We'll then derive the Cartesian equations from the polar equations. And then we'll also look at how we can derive the area within a cardioid and how that relates to the base circle. And lastly, we'll look at the perimeter of a cardioid and how also that relates to the base circle. So I hope you enjoy this session today. If you like our video, that would be really great. If you share it, that would be fantastic. If you subscribe to our channel, that will go a long way in giving us that extra motivation to keep going. So let's move forward and start on this journey. So we said that a cardioid is generated from a base circle drawn in orange, and when you have all these points that are equidistantly spaced, and then we choose a specific point, point A, and then we use these points that have been created as center points, and the radius, the distance from these specific points to point A. Then when you draw these circles, the envelope of the entire set of circles is what a cardioid is. So that's a cardioid, and the circle that generates the cardioid is a base circle. And then we keep moving forward, and we looked at also a cardioid being generated by one circle, the base circle, and a secondary circle that rolls around this base circle. And if we have a specific point on this secondary circle, the path traced by this specific point, this fixed point, is a cardioid. So this is the second way in which we looked as how we would generate a cardioid. So this is going to be just an introduction of what a cardioid is. If you have any questions, feel free to reach to us, and we'll love to expand on that. So next, we are going to see how to derive the polar coordinates of points P and also P prime that are on the cardioid. So if the circle shown here be the base circle, we previously in our previous video, the first video in the cardioid, saw that the points on the cardioid are a pedal. In other words, they are a reflection of the points on the circle, with the mirror being the tangent at points on the base circle. So Q being the point on which its tangent creates a mirror image of A at P. That means that AM, let's begin with AM. M is a point on the base circle, and the angle AMB can be derived from the fact that AB is the diameter, and so the angle AOB, O being the center point, is 180 degrees. So if the angle subtended at the center is twice the angle subtended at the circumference, it means that angle AMB is half of 180 degrees, which is 90. So you have a right angle triangle AMB, and so AB being the hypotenuse, angle the length of AM is going to be the diameter, which is 2r, r being the radius of the base circle. AM is going to be 2r cosine theta, right? And also previously we saw that the line PP prime is 4R with M being the center point. I refer you to our first video to see how that is the case. And so AM being 2R cosine theta, MP is going to be half of the 4R, which is 2R. So AP being AM plus MP, it means that now AM being 2R cosine theta, MP being 2R, AP becomes 2R times 1 plus cosine theta. So if we take A to be the center point, because this is where the cardioid loops and touches the base circle and loops out around, it means that X is going to be AP cosine theta, where AP is taken to be the radius or the length of the cardioid, the length from the center to the point on the cardioid, a specific point on the cardioid. So X is going to be 2R times 1 plus cosine theta, and Y is going to be the same radius of the cardioid, which is 2R plus times 1 plus cosine theta times sine theta. So these are the set of the polar equations that we do need, and we will take 2R times 1 plus cosine theta as the radius of the cardioid. So if you have any questions in this regard, please leave us a comment or a question in the comment section. We'll get back to you. So we do now have our polar equations, so let's move forward. So now we're going to use Desmos, and we're going to take advantage of parametric equations on Desmos, which is a graph plotting software. So as you can see here, we've placed the x-axis as 2R times 1 plus cosine t, and then the y-axis is 2R times 1 plus cosine t sine t. And so we've also put r as 2, and then we're going to vary that. And in order now to play around with the angle theta, we put that to be A, and as you can see, that is denoted by this point, this pink point that moves around. As the theta moves around, you see this point move around cardioid. And you could play around with the radius, and you see the size of the cardioid change when we move r around, r being the radius of the base circle. So that is simply how you can plot a cardioid, taking the polar equations that we had and using parametric equations in Desmos. You can pretty much plot a cardioid and derive the Cartesian equation of a cardioid from the polar equations. So we've now we have x being 2r times 1 plus cosine theta times cosine theta, and y being equal to 2r times 1 plus cosine theta times sine theta, right? So if we take x to be rho, and rho being the radius of the cardioid, rho here is, and then y being rho sine theta, where rho is taken to be the 2r times 1 plus cosine theta, shown here, which is also the same as x squared plus y squared square root. We can square both sides from this expression. So we have on the left hand side here, we have 4r squared times 1 plus cosine theta squared equals to x squared plus y squared. And then we can square again both sides so that we have 16r to the power 4 times 1 plus cosine theta squared times 1 plus cosine theta squared is equals to x squared plus y squared all squared. And so we can expand the second square here so that this becomes 1 plus 2 cosine theta plus cosine squared theta. And then we separate it a little bit in a way that 1 is the same as sine squared theta plus cosine squared theta. And so we can take the sine component on one side, and then we can bunch this cosine squared theta and this cosine squared theta. So we have 2 cosine theta plus 2 cosine squared theta. And so we have 16r to the power 4, 1 plus sine cosine theta squared times sine squared theta. So we've isolated this out here. And then we've also separated the 2 cosine theta plus 2 cosine squared theta and then multiplied to 16r to the power 4. So now we have 16r to the power 4 times 1 plus cosine theta squared times 2 cosine theta plus 2 cosine squared theta. This equals on the right hand side to x squared plus y squared all squared. So this part here is very easy to see that when you square y here, it becomes 4r squared 1 plus cosine theta squared sine squared theta. So this part here we can play around a little bit. Let's first of all remove the 2 on the second part of the left hand side so that 16r to the power 4 becomes 32r to the power 4, and then we can now go back and substitute the x and y back in place of the cosine theta and the sine theta. So this is what we know now, and we had come to a point where we have 16r to the power 4 times 1 plus cosine theta squared sine squared theta plus 34r to the power 4 times 1 plus cosine theta squared times 1 plus cosine theta times cosine theta. Yes, so we factored out the cosine theta. So let's look at the blue. The blue here can be looked at as the y side squared over 2r squared, which is 4r squared. And then the green part here can be looked at as simply x squared. So let's go and plug that in. I beg your pardon. So the green part here is similar to what we see here. So we've plugged back x squared plus y squared. And then in place of the blue, we have y over 2r all squared from this part here. So when you continue, we can also look at the second part here of 1 plus cosine theta cosine theta. And then we pull the 2r from the 8r squared, so we're left with 4r here. So we have 2r times 1 plus cosine theta times cosine theta, which is the same as x. So we substitute that back in, so we have x, and so now we have an equation that is entirely dependent on x and y, and also the radius r of the base circle. So we can rearrange things a little bit. So we have the Cartesian equation of a cardioid being x squared plus y squared all squared minus 4r squared y squared minus 4r times x squared plus y squared close bracket times x equals to 0. So this is the equation, the Cartesian equation of the cardioid. And so let's go forward and see how we can plot these using Desmos. So using Desmos, okay, so we're just going to put in x squared plus y squared close bracket squared minus 4. Let's use a in place of r, so we have 4a squared times y squared minus 4 a times x squared plus y squared close bracket times x equals to 0. And then we can vary r, since it's the radius, we create a slider. Let's set r to be equal to maybe from 1 to about 2, so that we'll see now a beating heart in a way. So when you play that, it's interesting. So you see the radius increase and decrease. Okay, so let's maybe change the color there from green. Let's just put black. I like black. So let's set it to black. And then we want to shade our circle, our cardioid, to look pink, like a heart, or red. So let's copy this equation, and then we create an inequality so that everything within that circle is shaded. We don't want black. Let's change that color to maybe pink or red as we wanted it. So yeah, let's use red. And so you can see a beautifully beating heart. That's the cardioid, right? So that's cool. So we see that we can use a Cartesian equation to plot this cardioid using decimals. Feel free to, this is a free online software. Just type in decimals on your Google and it could take you there, and you can play around with this equation. Preamble. How may we find the area of a cardioid knowing the radius, but also having the theta relationship, or the angle azimuthal relationship known. So if you have, for example, this perfect curve here, and you have radius and then you have theta, the area can be looked at. If theta is very small, you have a triangle, right? And so the area is half of the base, which is r theta, times the height, which is r. So that's how you may look at it. But generally the area of that sector where theta is very small is r squared over 2 theta. So how may we apply this to the cardioid? So we do have our radius being rho squared over 2, and theta being the small d theta. So we have a small angle that we are taking into consideration, and we are varying that from 0 to pi. And since the entire extent is 2 pi, we can just say, okay, we can look at half the cardioid, and then we're moving from, since it's symmetrical, we can look at it as twice the integral from 0 to 2 pi. And so we already know that our radius is 2r times 1 plus cosine theta. And so we'll substitute that in there, and there is this half and the 2, this would cancel out, and so we have 2r times 1 plus cosine theta all squared. We can pull out the 2r squared, which is 4r squared, and so we have 1 plus 2 cosine theta plus cos squared theta. And since cos squared theta is the same as cosine of 2 theta plus 1 over 2, we can substitute that back in there. So we have 4r squared times the integral from 0 to pi of 1 plus 2 cosine theta plus cosine 2 theta plus 1 all over 2. So this half here can be added to 1. So combining the half and the 1 becomes 3 over 2, and then we have 2 cosine theta plus 1 over 2 cosine 2 theta integrated from 0 to pi. So this becomes 3 over 2 theta plus 2 sine theta plus a quarter sine 2 theta, obviously from 0 to pi. And so applying the limits, we have 3 over 2 in the brackets, pi minus 0 plus 2 sine pi minus sine 0 plus a quarter sine 2 pi minus sine 0. So the sine pi and the sine 2 pi and sine 0 all tend to 0. So we're left with 3 over 2 times pi times 4r squared. This becomes 6 pi r squared. And so r being the radius of the base circle, the area of the cardioid generated from that base circle is going to be 6 pi r squared, which is interesting. So it's 6 times the area of the base circle, which is fantastic. Okay, so let's continue. Let's continue. So as a preamble to determining the length of the perimeter of the cardioid, if you have a curve, a regular curve like that, and you have, the radius at a specific point and the angle d theta, so obviously the arc length here is the perpendicular arc length is going to be r d theta. But also we have a dr here, so that by using Pythagoras theory, the length of the small arc here, the infinitesimally small length here, ds, is going to be the square root of the base, which is r d theta squared, plus the square of the height dr. So using this formula here, we can now go ahead and say, okay, we can integrate from 0 to pi, but since the cardioid is symmetrical, we can now just take twice the length. And so we have twice the integral from 0 to pi of the square root of the radius of the cardioid, which is rho, and d theta, the angle, and d rho. So we can then express d rho as d rho d theta times d theta, so that we can pull out the d theta out of the square root sign. And then we have to have the derivative of d rho with respect to theta substituted in there. Since rho is 2r plus cosine theta, then d rho d theta is going to be 2r times negative sine theta. So substituting those back in, so we're going to have twice the integral from theta equals to 0 to pi of 2r plus 1 plus cosine theta all squared plus 2r times sine theta all squared. So we can pull out the 2r, and that becomes, we have 4r, and then whatever is inside the square root sign, we have 1 plus 2 cosine theta plus cosine square theta plus sine square theta. Cosine square theta plus sine square theta is 1, so this can be added to 2 here. So we have 2 plus 2 cosine theta square root integrated from theta equals to 0 to pi times 4r. Then we can pull the 2 out, so we have 4 root 2r times the integral from theta equals to 0 to pi over the square root of 1 plus cosine theta. Now using the half angle formalism, cosine theta is the same as 2 cosine squared theta over 2 minus 1. And when we plug that in, the 1's cancel each other, positive 1, negative 1. And so we have 2 cosine squared theta over 2. And now we can pull that 2 out, so we have root 2, and then the square root of cosine squared theta becomes cosine theta over 2. So we have now 8r times the integral from 0 to theta equals 0 to theta equals to pi of cosine theta over 2, which is now easy to integrate, because that now is, we have 8r times 2 sine theta over 2 from 0 to pi. In that substituted, we have 2r times 2 sine pi over 2 minus 2 sine 0. Sine of pi over 2 is 1. So we do end up having 16r. And that is the perimeter or the length of the cardioid. So it doesn't depend on pi. It's just 16 times the radius of the base circle. So that brings us to the end of our treatment of the cardioid today. We'll keep going on with some of the properties and also the optical properties of a cardioid. Cardioid, believe you me, cardioid is a very interesting figure, but this is something we'll continue looking on, and hopefully we gain some inspiration from it. So until next time, have a fantastic time, be blessed, and stay locked. If you have any question, please leave it in the comment section. If you haven't subscribed, please subscribe to our channel. We do really need your support. If you can share, please share. If you don't mind liking, please like. That will help us a lot. Thank you. Bye-bye.